Yeah, sure. So the project idea was sort of built on top of something called Jacktrip, which was essentially created originally because of the coronavirus pandemic's effect on musicians and like musicians not being able to practice together in person. And the problem is like practicing together like online through like streaming typically doesn't work very well because the latencies are way too high. So like researchers at Stanford created Jacktrip, which is supposed to be like a low latency audio streaming application, which has like under, I believe like 30 millisecond latencies, which is like required for musicians to synchronize together. But the problem is like Jacktrip could be made easier for like most people to use by because right now it's like mainly like a command line interface application. So we wanted to make something that would be easy to just like use with like a microcontroller and just be available for like anyone to use. And so that sort of kicked off our project idea of using the PIC to use Jacktrip to send and receive audio through the internet, basically.
Cool.
Yeah. So there's some. So Jacktrip has been around for about 11 years, but it recently had a whole lot more interest starting last spring. So that's my first thing. And second thing is there are pre-built Raspberry Pi based virtual studio devices that use MDNS on home networks and provide some sort of plug-and-play experience, but the Pi is a full Linux machine, so it's not recommended to unplug. Like, they do mount the SD card read-only in those devices, but there are reports of corrupted SD cards, so we feel that having a proof of concept on a microcontroller, like, I think that the microcontroller, it's a lot harder to corrupt the program memory, and you can really pare down all the stuff that you don't need from Linux. So, any questions about the premise? Oh yeah, so we use the internal ADC of the PIC, the 10-bit ADC, and we use the DAC provided as part of the big board. We transmit mono audio at 48 kilohertz with 64 frames, so 64 samples per packet. So those are the technical specs, and that means you have about 2.67 milliseconds of latency at the floor. So the Pi probably has a bit more of that than that because of overhead, but I believe that the PIC is like right down on that floor because everything we do is based on hardware counters. So without further ado, any questions on anything that Ben or I said?
So the protocol is a variant on UDP then?
Yes. So there is let's see, 8, 9, 10, 11, 12. There's a 16-byte packet header that has a timestamp, a sequence number, and stuff basically saying what kind of audio it has. And then there's audio data, and it's uncompressed. It's just their 16-bit format is literally just the signed fract that our ADC gives out, so it's standard fixed point.
Mm-hmm.
And yeah, there was a TCP protocol at one point, but that was too slow, so they got rid of it.
So could you, I know you just explained this but I want to make sure I understand it. Could you just walk me through the data path once? Like the pieces of hardware through which the data passes in the system?
Absolutely. So, we have the analog input, which right now is connected to the speaker output, headphone output of the computer. That goes to, I believe it's channel 0 of analog. It goes to whatever the LED pin is on. I think that's on A0. And then that's sampled by the ADC, which is on the timer 3 interrupt for 48 kilohertz sample rate. Then the ADC done event triggers a DMA transfer of that sample. And then the block size is 128 bytes for that DMA sample, because that's 64 16-bit fracts going into the packet. So we turned on the DMA done, block transfer done interrupt that signals the Ethernet code to send a packet out. So once all the audio is loaded into the packet, we double buffer the packets. So the packet that we're loading isn't the one that we're sending out over Ethernet. And we found that, and I think there's some weird issues with aliasing, so we weren't quite able to do that fully. But
Gotcha.
that's the audio path coming out and coming in. It's basically reverse. We get packets, and then we double buffer the received packets. So when a packet comes in, we start playing from the other one. And in that timer 3, it serves two functions. One is to tell the ADC to sample. The other one is, if there's something that we want to play, we need to output it to the DAC. And we found that in ISR, the conversion from the fract to the 12-bit format that the DAC wants is not too computationally intensive. It's just a bit flip and a shift. So we just did that in ISR, and it worked.
Okay, awesome. Thank you.
So let's go ahead. I'm going to demonstrate receiving first, because that is most useful. So or not most useful. That's what works the best. So I'm going to go ahead and share just my full desktop, but not share the Zoom window. Let me just get off of the Zoom window on the okay, so I'm sharing my full desktop so that I can show you kind of what's going on here. So we have a window here that is jack trip coming from the PIC. Then over here we have jack trip coming from my Linux computer over here that we can test. It has a mic hooked up to it. And then we have nload here looking, just look at that. We're getting about 850 kilobits out and over a megabit in, which the original library wasn't able to do that. We were only able to get like 600 to 650 kilobits bidirectional, so we did make a substantial improvement there. So we can just make our connections in the patch bay to do our receiving. So we shall go ahead and let's go ahead and connect my Linux computer to the PIC. And then we can go over to there, and then let's make sure that's still going. Okay, so red channel B is what's coming in. So you can see my voice is on the scope now, and it's also showing up on. Actually, wait, no. Which one is? Okay, one of them is my voice. Let me go ahead. Actually, channel A is the input. No, channel B is the output. Channel A is the input to the PIC. Channel B is the output from the DAC that's going in. So I'm gonna stop sharing so that I can unmute and you can hear how my voice sounds on Jack Trip. Go ahead and mute here from my studio mic.
Kind of hearing me, it's distorted, but you're hearing me now through this mic over Jack Trip, over the Ethernet to the PIC, and then out the back into Xing. So it's not perfect, and we can like I think due to the precision on the internal RC oscillator, there's some frequency distortion. So if we put in something like a nice pop piece. So yeah, there's a little bit of distortion and a little more like complicated piece, a little bit of organ music, and it's practically unrecognizable in our proof of concept, but I think that might be the internal RC precision. See, here's some organ music. See, that clip is barely recognizable. And then here is just some tones generated to demonstrate that there is a frequency issue. So yeah, you have to go up to like 1100 hertz to go up an octave from 421 hertz. So
That is very cool.
So it's
I'm gonna go ahead and mute here and go back to my better mic if we're gonna talk more.
And I'm back on the better mic.
so it sounds like a little bit of overload someplace, like something saturating or overflowing someplace. There's lots of steps where it could do that, right?
Yeah, so one thing that happens is we don't do anything with the sequence numbers, so it could be, I know that Wi-Fi from this computer to the access point in the dorms and Wi-Fi in the lab to where the Raspberry Pi is, there's dropped packets. There's plenty of dropped packets, and the PIC doesn't do anything to reorder or delay or set to zero the dropped packets, just because we didn't have time to implement that part of their reconstruction algorithm.
That would explain that kind of just frequent, because it was clear that the distortion was related to the frequency directly.
Yeah.
So it's signal related. Okay.
Yeah, and then real quick, I do want to demonstrate what you hear with the transmission. So I'm gonna go ahead and let's see, get the zoom window off of there for a second. I can go and demonstrate what it is I'm doing. So I am disconnecting my laptop from there, and I'm just going to loop back the jack trip on the PIC. So that zoom window is not supposed to be in the background there. Let's boot that off. So back to, so now we have so what's on channel A, what's on channel B. So A is coming from the computer to the PIC, B is coming out from the PIC. So
Okay.
We are looping back, and if everyone just be quiet for a little bit, I'll stop my share and just demonstrate. So I am going to unmute. So, like, what you're going to hear is just aliasing. So I think that something on the transmit side is getting like overloaded when we have the Ethernet stuff running.
Interesting. You're muted, Bruce.
I thought I could hear some out of order stuff there, in fact, because it seemed like there was some scalloping in the frequency changes as you went down in frequency, which would explain some of the noise if it were in fact some out of order packets.
Yeah, there's that. There's also, I wonder whether it could be an aliasing problem because as we're going up and up in linear frequency is going whoa 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 whoa. So there could be something with that. And the last thing that I want to demonstrate is, like the PIC is able to sample at 48 kilohertz. It's not able to do the loopback on the network, but here's just a demonstration of local loopback that is a different program that doesn't have the Ethernet on it. So it's just making program that project. So now we are looping back. Yeah, now we're looping back. So if everyone just be quiet to minimize the chance of feedback. I'm gonna unmute on the lab computer again. So, I mean, that sounds like 10-bit ADC and 12-bit DAC, but for a device that theoretically would be under $20 for the hardware, I think the goal of having an easy device that's inclusive of everyone would be useful there. So yeah, that's just my demonstration of just looping back, not doing Ethernet at all. And you notice we could use a little better shielding. We could have shielded the analog connections better, because I think we're hearing the chip select lines in particular when we run the Ethernet and stuff.
Yeah.
Very cool. That is an
Wow.
impressive amount of infrastructure.